If you enjoy Astronomy FM radio, please let us know with a small donation. We do rely on your support, and it's true. Every little bit counts.
AFM. You are listening to a universe of possibilities. This is Astronomy FM.
Coming up next, an Astronomy.fm original program. It's time for York Universe, a co-production of the Observatory of York University, Toronto, and the Voice of Astronomy. AFM Radio, AFM Radio, AFM Radio, AFM Radio.
Hello, everybody, and welcome to York Universe, the Astronomy and Astrophysics.
If you enjoy astronomy,
AFM Radio, AFM Radio, AFM Radio, AFM Radio.
Hello, everybody, and welcome to York Universe, the Astronomy and Astrophysics program written and presented by the students, faculty, alumni, and awesome friends of York University in Toronto. I am one of your hosts tonight. My name is Jesse, and I'm joined with Richard. Hello, Richard.
Hello. And
we are, of course, broadcasting live from your friendly neighborhood York University Astronomical Observatory in Toronto, Canada. Tonight, of course, is Monday nights on AFM is Astronomy Night in Canada. So the entire programming here is Canadian, starting with us, York Universe. Then we move on to Western Worlds, which has got a great connection to Toronto, and we'll talk about that. 365 Days of Astronomy, Quirks and Quarks, Science for the People. It's all Canadian, all night. It's great country, great astronomy coming out of it, so stay tuned. Tonight, of course, York Universe broadcasts every Monday night at 9 p.m. local Toronto time, or Tuesday morning at 1 a.m. It's 1 a.m. right now. I think we're on daylight savings time, Universe Coordinated Time. This production you're listening to is actually working in concert with another live program. So we're live right now, but we're also live at the York University Astronomical Observatory website for something that we call online public viewing. It's a really great program. If you have not the means to visit a telescope in person and look through the eyepiece of a telescope in person, we can do that for you virtually. So if you go to our website, which is astronomy.blog.yorku.ca, I think it's right now, you can log in, or if not, it'll be up in a few seconds. You can log in and you can actually join a chat room that has a virtual view through our observatory. So take a look at that. It's really cool. Everything we do here online, on air, this broadcast is entirely powered by and partnership with the Voice of Astronomy, AFM. If you ever have any questions, you can find us at our website, on Facebook, on Twitter, and all over, all that great stuff. So thanks for tuning in tonight. Now, before we dive in, I already introduced Richard. Richard, you doing good?
Yeah, I'm still here.
You're still there? See,
yeah,
Richard,
still enjoying the speech.
Yeah, I know. We have so much to say. But see, the nice thing about tonight, Richard, is that we have a guest. And now, we don't get guests all the time. We have guests once in a while, but this is a very, very special guest. This gentleman used to be a host of York University. He was probably one of the original hosts, if you really take it back, in the early years of the program. His name is Dr. John Moores. He's now an assistant professor of Earth and Space Science and Engineering at York University. So he's part of our group. He's actually cross-appointed into physics and astronomy. Before all that, he did his bachelor's at University of Toronto, got engineering science. He did a PhD at the University of Arizona. He's a participating scientist on the Mars Science Laboratory, or affectionately known as Curiosity. He contributed to the Mir rover, so Spirit and Opportunity. He was on the Huygens mission, the Phoenix mission. He's currently running the Planetary Volatiles Laboratory at York U. He was a host here on York Universe and developed the program Western Worlds, also known as Dr. John. Welcome.
You're making me blush, Jesse.
Well, it's not my fault. You have a really long resume.
Well, it's been a lot of fun the last few years especially. I've got to say,
The crazy thing, John, sorry to cut you off. The crazy thing is that you did most of that before you even became a professor.
well, certainly, some of it. You've got to make a little bit of noise, I think.
Sounds like that's what I've always heard, sort of from you and from other people, is when you finish your PhD, and once you finish the PhD, if you want to be a professor, you got to start making noise, right? And so you join on big projects, you write a lot of papers, you get involved with a lot of stuff, and you really boost up your resume.
Oh, yeah, you've got to stay active. You've got to get out there into the community and make a contribution. And not just in the scientific world, but also in public outreach. And this is a great venue here at AFM, always has been.
Oh, see, for those listening, we started this program a long, long time ago. There was Paul Delaney, there was Robert Berthium, there was me. I can't remember who else. You were involved in the early days as well, and it really has. I don't know. You logging in now and joining back in because you haven't been on in a while. Has it changed for you? Listening to the first 5 minutes here, is it any different?
No, it brings back some memories.
Hopefully, good.
Oh yes. It's great to hear those sonorous tones of your voice again, Jesse.
Oh, you're far too kind. Thank you very much. And Richard is a new host. Richard, how are you liking York Universe so far?
It's fun. It's a good way to spend a Monday evening.
Have we been on a show together, Richard, you and I? Maybe once, eh?
Yeah, I think once, like a long time ago.
Oh, man.
Yeah.
I can't even remember. Sorry, I'm just logging in. I finally got into the chat room there. It looks like it'll be up in just a little bit at the astronomy.blog.yorku.ca. All right. So, sports fans, what we're doing tonight, John is a guest, but he's also a host, both of York Universe in the past, and developed a program called Western Worlds. John, do you want to give us just a quick roundup of what Western Worlds, the feel of Western Worlds is all about?
Well, I think we used to say it was a lot like we definitely owe a lot of heritage and a great debt to this program, York Universe. But we felt we added a little bit of a tie. We edited it up. We had our round tables and our interviews that we put together with a little bit of fun music. So we thought it was a good compliment.
I 100% agree. We have this sort of live feel at York Universe, and you branched off when you head off to Western University or University of Western Ontario, and you did a whole the same sort of idea, but with a whole different feel. And I really I've listened to it a few times, and I really enjoy the panel discussions where it's one topic with a few experts, and you get a bunch of people hammering at one topic. And I really like that.
Still, there's nothing like live radio. I've got to say. I mean, that's the miracle of editing with Western Worlds is that anything that you say, any hesitation, that's all on the cutting room floor. But here you get exactly what we're saying.
So you can see just how much we hesitate, everyone. That's the great thing about this live radio.
Oh, you must never hesitate, Jesse.
I never do, really. That's true. All right. So normally what we do is we start off with This Week in Space and Astronomy History, and I'll start us off. Feel free to jump in here, sports fans, and contribute what you like, but I'll give us the start here. This is one of my favorite topics in recent science because it sort of shows the process of science. So May 29th, that was yesterday. Yeah, today's May 30th. So May 29th, back in 1919, we're not nearing on the 100th anniversary of this. We're very close to it. This was when the science world got to make the first real test of Einstein's general theory of relativity. Now, we've all heard of this. We've all heard of Einstein being the relativity guy, and that whole theory of both special and general relativity is basically saying that the way you measure speed, the way you measure mass, the way you measure time and energy is very much dependent on the relative frame of reference you're in. And it was a theoretical work. It was a theoretical physics work that he developed, and it was very brilliant. But he also offered testable predictions, and that's the real key when you're doing science. Is if you're going to generate a theory, you got to make a testable prediction. And his theory of general relativity predicted that the fabric of space-time, when bent by mass, would also change the trajectory of a light beam. So if light was traveling through space and the fabric of space-time was bent, it would follow that curve. Now, that's a great thing to say, but a difficult thing to test. And in 1919, there happened to be a great chance to do this, and this was during a solar eclipse. The best place to view it was, I believe, in northern Africa. And what physicists did is they waited until the totality of the solar eclipse, where the moon was completely covering the sun, and took images of where all the stars were near the sun, and then waited later until the sun and the moon were no longer in that position, and took again pictures of that same star field and compared the two. And if Einstein's theory of general relativity was correct, the mass of the sun in between the stars would change the position of the stars on the sky as compared to when the sun wasn't there in that place in the sky. And that's what they did, and they proved it to be correct. And the cool thing about this is that the actual person who conducted this expedition was Arthur Eddington, who is one of the greatest contributors to early astronomy. He did so many things, was an expert in Einstein's relativity, among many others, and so basically made the first experimental test to prove that Einstein was onto something really big. So I really like this story. I don't know if you guys have anything else to add to that.
Yeah, actually, it's pretty cool. And I think, I mean, correct me if I'm wrong, but Arthur Eddington, because 1919 was just after World War One, and
Yep.
I think he was the guy who was allowed to continue doing scientific research because in World War One, when they were conscripting people, there was a really brilliant physicist named Henry Moseley, who was killed during the war, and he was kind of like a prodigy, and his work had far-reaching consequences, especially in chemistry. And because of his death, which kind of ticked off the scientific community, and I think Rutherford was lobbying the English government to stop sending its scientists to war, and Eddington kind of was on the receiving end of that and was allowed to continue working instead of end up potentially being conscripted, and surviving the war, being able to conduct this experiment. It's kind of like a neat little historical tidbit. Science never occurs in a vacuum.
Holy, Richard, I had no idea that story existed. That's a
Oh.
really cool piece of history.
Yeah, now I hope I got all the details right.
Well,
Yeah,
if the broad strokes are correct, I'm happy.
Yeah, I'm fairly certain I've read that before.
Yeah, that matches up with the Isaac Asimov write-up that I read just a few days ago, actually. He did actually do nonfiction, too, I should mention.
Eddington?
Asimov.
Oh, sorry. Asimov did a nonfiction, like, sort of historical account of this?
Yeah, he also did quite a few scientific essays as well. And being a scientist himself, the PhD from Columbia, he was well positioned to do it. And the story of Moseley was one of those.
Oh,
So
wow.
now that makes me think, because John, you are probably the most well-versed science fiction reader I've ever met. He's got a blog about it, people, just an FYI. Is there any other examples of famous scientists, famous physicists or astronomers or biologists or chemists that also have dabbled in those really great works of science fiction?
There are plenty of other examples. I wouldn't say I'm the best read. I'm sure that there are many people listening here tonight who could easily best me on that.
That I know.
But you think of other people who bring their knowledge with them. Folks like Larry Niven, for instance, a mathematician, and you think of some of the things that he came up with. And we've got folks like Arthur C. Clarke, a favorite of Paul Delaney.
Oh yes. So there's lots of good examples, and this story, as accounted by Asimov of Moseley, talking about how Eddington got to stay out of the war because there's too many scientists being sent to war. That's a really interesting one.
Well, more about Moseley itself and sort of where his career was headed at the time. And of course, the Second World War was very, very different, and scientists had a very different place in that one.
Oh yes, yeah, they played. They were almost central to it in a lot of ways.
Indeed.
So there you go, people. There's the story of the 1919 solar eclipse that proved Einstein to be correct. Of course, that didn't end the probing into Einstein's general theory of relativity. Of course, very famous news over the last few months was the LIGO results and the gravitational waves, which is also a prediction of general relativity. So even 100 years later, we're still confirming GR to be true, which is what you need to do in science, and you need to keep looking down these avenues. But that first step down that direction was back in 1919. Very good piece of This Week in History. Should we move on, Richard? You want to do the next one?
Yeah, sure. So the next one is May 25th, 2008. It's almost a century later and totally unrelated. The Phoenix lander touched down in the polar region of Mars. So Phoenix was, yay, go Mars, was obviously a lander, and it was sent to Mars to kind of look for environments that were suitable to life, like small bacterial, microbial life, not obviously Martians, and to see the situation with water, if there's any evidence of history of water. And it touched down May 5th, 2008, and it was also the first probe to be successfully landed in the polar region of Mars. So its primary mission was done in August, and we kind of lost contact with it shortly after. There was some contact in up to, I think, in November, and the mission kind of ended, or was declared to have ended, on November 10th of the same year, 2008, because NASA wasn't able to recontact the probe anymore. So short but sweet, but it did manage to complete its mission, which is good news for any thing that you send to another planet. Sorry, and it did discover water ice below the surface of Mars, and that snow falls and dust devils, because why not?
I mean, there's tons of videos. I think dust devils were discovered as far back as the early missions in the 70s. But John, this is your bread and butter. This is the Phoenix lander landing in 2008. I was actually at York University at that time. I had just started there a few months earlier, and I absolutely knew nothing about it. And I remember it being such big news. What was it like being part of that mission?
Yeah, it was exciting. I was a grad student at the time, so we overlapped just a little bit there, I think. And,
really? I didn't know that.
I'm afraid so.
Cool.
And I was working with Peter Smith at the time, who was the principal investigator, and this was down in Tucson in Arizona. And it's always exciting when the landing is happening. Everyone is crowded around the screens, just waiting for news. And the way it is, I mean, with those 7 minutes of terror going through the atmosphere, you don't know what's going to happen, and whatever has happened already, it's already taken place because of the light time delay. So there's nothing that you can do. You just listen for the telemetry to come back, and you hope that it's good. There's always a big cheer when the parachute opens, and then when we have confirmation that we're on the surface, that is a great moment. But the biggest cheers often are saved for that first image, that first view of a new world. And that's why a lot of us do this, to see that place never before viewed by human eyes.
So, of all the cool stuff that the Phoenix did, what was your favorite result? Favorite scientific paper, I guess. Favorite scientific result, and you can of course choose your own work if you like.
Well, I mean, the snow is really neat. And I helped out a little bit with that paper, which was led by York University, which is fantastic.
Oh, awesome.
And that's also the first use of an atmospheric LiDAR on another planet. So an amazing new technique, a new technology, and we've been going on from there.
I actually remember you giving a presentation, I think it must have been you, at one of the journal clubs at some point showing, there's video, right? There's video of clouds and snow falling, that have been patched together from all the images, right?
That's right. I had a couple of roles on the mission. So I had what we call an operational role, so involved with the process of deciding what the spacecraft does every day. And the role that I had was something called the Science Planner Integrator. So what that person does is it kind of they take the science team's requests and they look at what the engineers know the rover can actually do, and you find a way to square that circle, which is great from my experience. In terms of the science, what I was doing was looking at the atmosphere using the surface stereo imager. And when we fired off the laser on the LiDAR a couple of times, we took images just to see if we could catch it. It turns out you can. You can actually see the light that's scattered off all of the fog particles in the atmosphere. And that was a fun paper to write up as well.
It's crazy. It snows on other worlds. I mean, it's not just crazy freak snowstorms you get here in Canada and around the world, but you can get them on Mars and potentially other places.
Planetary atmospheres are, that to me is an exciting field. Not just all the great stuff going on exoplanets, but you heard a few weeks ago from Christina Smith talking about fog on Titan, and we were talking about Mars here. It's an exciting field.
Yeah, really rich, and there's and it seems to be, and it's been something that we've studied for so long, but it also seems to be just coming into its own, is, if I could say that. I mean, I'm obviously not an expert in the field, and I've only been around for a little bit, but the amount of scientific instruments on the ground in orbit is like doubled and tripled in recent years, and it's really sort of blowing the door wide open.
Yeah, the ground is really exciting. I'm one of the people who mainly works with ground assets. Most of the people who do it working with telescopes. The atmosphere being right there, easiest things to study. It's essentially that boundary between the planet and space. And so you can learn an awful lot about a planet from its atmosphere, what it's made of, what kind of processes went on, what kind of dynamics it has. So you learn a lot about what a place is like as a world and what it's been through by studying that sort of gassy haze.
Okay, I have a million questions, and I'm pretty sure, Richard, you do too, probably. But I'm determined to get through this week in history first before we dive into really probing the mind of Dr. John. So if you're just tuning in, everybody, you're listening to York Universe. Tonight you have myself, Jesse, and Richard, and guest starring Dr. John from York University. We're still in the middle of astronomy, or This Week in Space. The next one I have is another one for John, actually. This is the May 25th, same day, but 3 years later, after the Phoenix lander touched down, the NASA JPL group stopped looking, declared it completely over. The Spirit opportunity was dead and no longer would be found. This was after a good amount of time was spent with Spirit looking for it or waiting for it to wake up. And the long story short is that Spirit found itself unfortunately marooned in a rather sandy area, got stuck, sort of. It's happened to all of us. It's snow and sand and stuff with our cars once in a while, except there's nobody there to push its Spirit out. So Spirit got stuck, and then after a while ran out of power because of either dust or winter was setting in on, and so the solar panels can't generate enough power, and it just wasn't able to wake up. And they pinged it, and they waited a good amount of time, but eventually had to declare Spirit to be unsalvageable. Now, I will say that the great thing about that mission, that's 2011 when they're saying that they can no longer use Spirit, but it touched down in 2000. Was it 2003, John?
Early 2004.
Early 2004, it landed. So this is a mission that lasted 7 good long years here on Earth. That was only meant to last 90 days. And we all know the story of Spirit and Opportunity, the little rovers that could. And as Paul Delaney would say, they're the little rovers that did, because they contributed so much work to our understanding of Mars. And just to name a few, they worked on dust devils, they worked on water. They're working on the volcanic history of Mars, atmospheric stuff, water, what rocks look like when they're deposited in water-rich scenarios, all these different kinds of things, and eventually assets as you call them, John, are gonna hit their wear and tear. They're gonna hit a rock in the road and not be able to be used anymore. And Spirit found that in 2011, unfortunately.
Well, it's one of the fun things with the space engineering side of the business. It's, how do you keep something working long past its design lifetime? And, there's a lot of creativity that goes into that.
I can only imagine. I have had 1.5 cars in my life. I guess the first car was actually my parents' car, and then I had my own car, and the amount of work that required to keep that thing on the road was, well, a part-time job, and to keep a little robot working for 7 years without being able to go there with a wrench. I don't know how that. Yeah, it must be interesting to sit in the room and hear the different scenarios and problem solving that goes on.
Yeah, it's one of the fun things, and it's one of the privileges of the job. With Spirit, that hits close to home. I was never a member of the science team for Spirit, but it's where I did my training back in 2004. So it's sort of the first mission that I got to see up close from the inside.
I love Spirit and Opportunity. They have lots of great comics. Online comics have been written about them, and they have a fun Twitter feed. Very, very great rovers. They contributed so much. Unfortunately, we lost one, but we still got Opportunity. What's Opportunity doing nowadays?
So I've got to admit, I have not been following Opportunity closely. That's one thing about a mission, as it gets further and further along. The discoveries just start to stack up, and with what I've been doing with MSL and some of the other stuff, it's been hard to tear myself away.
Fair enough. We don't hold it against you. Okay. Why don't we move on to the next This Week in History? You got Richard, right?
Yep, it's me. So next, actually, this is today anniversary, May 30th, but 1966, the launch of Surveyor 1, which Surveyor 1 was the first of the Surveyor program, which was many different probes. But Surveyor 1 was the first American lander to land on another celestial body. In this case, it was the moon. It was sent up to, it mainly took pictures. It took like over 10,000 pictures of the lunar surface. It didn't have exactly scientific instruments the way you would on a probe that we send to Mars nowadays. But back then, 1966, there was a lot we still didn't know about the moon and its surface and the conditions there. And keeping in mind that the plan was to be sending humans there relatively shortly, you kind of wanted to know everything that you could about it, including, the landing sites that you're going to be putting people onto. So Surveyor 1 was up there, and it operated from when it landed, which was beginning of June 1966 until January 1967. Just NASA was constantly receiving images of the moon. And they were able to tell a bunch of different things about the lunar surface, First of all, obviously, what it looked like, what kind of stuff was there, the strength of the surface to kind of withstand weight, because you need to know that when you're putting people down there, temperatures on the surface of the moon, and later Surveyor probes that ended up landing on the moon did carry scientific instruments to, get further information. But Surveyor 1 was the first, and it was kind of like a milestone in the American space program and the unmanned space probe situation. And yeah, here it is. There's 11,237 photos sent to Earth.
So as many as I take of my dinner each night.
Yeah, there you go. It was the original Instagram, but yeah, it was quite a probe.
Something I always enjoy, and my poor Nats class always gets this question. So the moon is very unique in some ways in that the first lunar orbiter actually came after the first lunar lander. We normally think of orbiting a satellite first and then only later landing on it. There's actually one other body in the solar system that shares that distinction.
Wait, I can get it. Titan.
Titan is correct.
Yes.
Yeah, it's one of the interesting things with early exploration. And in '66, the Russians and the Americans were neck and neck, and Luna 9 only beat Surveyor 1 by a few months for the first lander.
Luna 9's being the USSR's?
That's right.
So the USSR landed a few months before in 1966. They were still neck and neck at that time, and then the United States pulled away. I guess in about '68 they started pulling away because the USSR started having a few technical difficulties.
It's true, but in some areas, the Soviets made some very important contributions even later on. We've got like the first planetary rover. Actually, in terms of a robotic rover, we normally think of spacecraft like Spirit and Opportunity, or maybe Surveyor. But back in the 70s, we had the Lunokhod rovers that traveled very long distances. Only recently has Opportunity actually surpassed the kilometers and kilometers of lunar surface eaten up by those vehicles. And the first robotic sample return as well.
They did the first robotic sample return of what?
Oh, from the moon.
I didn't know they did that. A robotic one?
Yeah, way back in the day.
Wow. The early planetary research going on. It always kills me the amount of work we were doing in the early 60s. Like the first satellite was launched in the late 50s. That was the first time humans ever went to space. And then, that's 10 years later, we're at Mars and exploded out there real quickly.
Oh, yeah.
All right, last one. We have one more this week in history. May 30th, that's today as well, 1975. Admittedly, I don't know much about this one, but it is a very important milestone. It's the actual establishment of the European Space Agency, and that happened when they merged two individual organizations, which was the European Space Research Organization, or ESRO, merging with the European Launch Development Organization, ELDO. And you put those together into a single organization, and that made the ESA back in 1975. So we're just 40 years over, 40 years since that was put together. 10 member states at its formation, and so this was following the establishment of space agencies around the world. We had NASA and we had the CSA coming into its own. Well, NASA had already grew into a superpower, and CSA was growing into its own, and then you have the ESA coming onto the block. So that happened just over 40 years ago, 41 years ago, I guess, back May 30th, 1975. Am I, just a quick question technical-wise, am I a little delayed here, everybody?
Oh, you sound good to me, although the Canadian Space Agency wasn't formed until 1990, so that is a little delayed.
1990? They were doing work way before that.
Yeah, but not organized into a space agency.
Oh my gosh, I didn't know that. 1990. Wow, that took us a while.
Indeed, it did, but we've been making up for lost time, I like to think.
No kidding. I guess what I'm thinking about all the contributions that were made to sort of the shuttle program from the Canadian robotics companies, and I just assumed that it was operated through some government-based research agency. But I guess if it wasn't fully organized and named, then it technically wasn't the CSA.
Do we know who built was it the Alouette? Like, we were way early on, we had a satellite in space after the Russians.
It was like 62 or something?
Yeah, so I guess was that not the government, or was that just some weird random non-space agency?
No, it was government-based. So launched in 1962, scientific... it's scientists
the
at
Defense Research Development Corporation, which is in Downsview, and a part of, if memory serves here, it's part of the Canadian Forces.
That makes sense.
Oh, okay.
All right, everyone. Thanks for tuning in, everybody. You're listening to York University. You got myself, Jesse, and Richard, and John, Dr. John, joining us. Hasn't been on the program in a while, and he's being a wicked guest for us. And we're going to dive in a little bit more on what John does. Now, John, you run the Planetary Volatiles Lab at York University. What is a Planetary Volatiles Lab?
So we're interested in the atmospheres, and we're interested in the interactions between the atmospheres and the surface, how the atmosphere changes the surface, and how the surface changes the atmosphere. So you can see sort of the evidence of past processes in an atmosphere, and you can think of things like sand dunes and other what we call aeolian features, where the atmosphere has an effect on the surface itself. So the collective name in sort of planetary spheres for this, for anything that is able to evaporate and to move into the atmosphere, we call that volatile. And so the name was available. We decided for my research group and our little lab that we have at York that we would call it the Planetary Volatiles Lab.
So you're studying how things evaporate, move, and the interaction between the atmosphere and the ground. How do you do that for? I could see how you could do that for Earth. I mean, you can go outside and see how water evaporates into our atmosphere. But how do you do that for any other planet?
The short answer is any which way we can.
Okay.
So what we do is we work with spacecraft and data sets available from NASA and other space agencies. We do participate with the Mars Science Lab, which means that we help out with operations, and we also do science, mainly using the cameras for something called atmospheric optics. You can get an idea of what the particles are that are suspended in the atmosphere using those cameras. We also do numerical modeling. A postdoc of mine, Dr. Christina Smith, just had a paper published looking at the optics of the titanium atmosphere from Cassini-Huygens, a mission that I was on way, way back in 2005. And really, if there's a way to investigate it, we'll go after it. We have a little simulation chamber in which we can recreate the surface and atmosphere interface on another planet. And I've got some undergrads working in my lab now who are looking at orbital images of clouds. So really, we're interested in the entire solar system, and now with some of my collaborations with Ray J. Ward Hanna, we're hoping to expand our territory out to other planetary systems across the galaxy.
Okay, I have so many questions now. Let's put a pin in that in your expanding out into the other planetary systems, because that's a huge topic. I'm interested first in, let's talk about the simulations that you have. So you are in a lab at York University, and you are able to simulate a other planet's environment. How do you do that?
Well, it depends on what that other environment is like.
Well, let's say Mars.
For Mars, you need it cold, by and large. If you wanted to use room temperature, that only works for a couple of hours out of the day near the equator at the right time of year. But for most of the planet, most of the time, you need it cold. You also need to dial back the pressure. The pressure of the Martian atmosphere is quite a bit lower than on the Earth. On average, it's about 0.6% of the pressure that we have on the Earth, something that planetary scientists would call 6 millibars, or 6/1000th of the terrestrial atmosphere. And you've got to change the composition as well. It's not nice oxygen and nitrogen like we have here. It's mostly carbon dioxide. So you mix those ingredients in there, you get it nice and cold, you get the pressure down low, you change the gas to carbon dioxide, and you've got a pretty good simulation of the Martian atmosphere.
So I guess it's pretty close, but it's not completely accurate. I mean, is there any way what you're saying is the science coming out of your simulation? Can anybody just say, but it's not a real Martian environment? How can we see if these results are real or not?
Well, the great thing about it, and we were talking a little bit earlier about how hard it is to bring back data from spacecraft. I mean, you only get a little trickle. MSL is a mission on which I just feel like we have an embarrassment of riches, because we have the ability to bring home something like 500 megabits per day, or a little under 100 megabytes per day, which is a huge amount of data. It's still, not, you can't have every picture you want. And you can't ask every question that you would want to of the environment. Plus, because it's a rover and it's doing a lot of different things, and it can't do science 24/7, you need to be very judicious about which questions you investigate, how you use that asset. And so the advantage of having a simulation of a little piece of Mars on the Earth that we can take as many pictures of as we want. We can wheel in any kind of instrument or equipment that we want to investigate that little simulated piece of Mars. We know we can ask of our little simulation the kinds of questions that we should then go and ask the real Mars. So it helps us figure out, what are the right questions even to ask on other planetary surfaces.
And it also, I know that, so not only do you simulate environments like that, and you are able to ask some questions and sort of frame how you're going to go after stuff elsewhere, you also do other kinds of simulations, mission-based simulations, where you're learning how to run a mission, where you'll go out with somewhere on Earth somewhere and actually do pretend missions, and sort of plan out that whole process on how you do your science, how you move the rover around, how does all that stuff work. And it seems like it's in your field, the simulation side of things is really, really important.
Well, definitely. And I mean, you want to make sure everything works well when you get the chance to do it. You don't want to lose any science to not having, not knowing the right way to go about doing it. I haven't been involved in what we call analog missions, which are these sort of dry runs, you can call them, or simulations on the Earth, for a few years. When I was at Western, back when I was a postdoctoral fellow, we were very good at that.
Yeah, I remember I almost got to join in on you, and I couldn't help out. But um, this kind of thing, this whole like simulating what you're doing is really cool because for me, as a quasar astronomer, the simulations are very, very helpful for me to shape how I'm doing my research. So a quasar's accretion disk, I have a general idea of what a theorist would tell me or a simulator would tell me an accretion disk looks like, and I can see if that works in my actual data that I go get with a telescope. That give and take between the two is really, really important, I find.
And I think it's kind of the same for us. We get observations back. We don't always understand exactly what they're telling us right away. And you may need to run a simulation in the lab. You may need to run a simulation in a computer to really understand the significance of that observation. And just like we were talking about Einstein earlier, often those laboratory and computer simulations make predictions that we can then follow up on with that same space asset.
Okay, so now I want to expand this a little bigger. So you're interested in the climate. You're interested in the boundary at the surface. And you also, as a very layperson in atmospheric science, I find it whenever I read information about or read stories or research about the Martians' past history, the Martians' past or Mars's past climate, how can you actually, I know this is a big question, how can you predict what the atmosphere was like 3 billion years ago?
Well, that's a challenge. So you look for things that are consistent. So we see a lot of things on the surface that look like they were cut by liquid water, for instance.
Right.
So to get that, the atmosphere must have had to be substantial enough that you could have water flowing for long enough to cut those features. And when we look at the water story on Mars, the atmosphere tells us quite a bit about it. We see that the atmosphere looks like it's a lot of it has been lost to space, and we can tell that by looking at the different molecules that exist in the atmosphere and the balance between them. A lot of what many atmospheric chemists do is they want really fine measurements of exactly how much of this isotope and how much of that isotope because of the way they behave in the environment. And you can tease out all sorts of things like how much volcanism has taken place, at what times, what's happened to the water inventories. You can even find out whether or not the atmosphere came outgassed from the interior of the planet or was collected from the solar nebula or from initial accretion. So there's a lot of interesting things that the atmosphere can tell us about where the planet has been as a complete system.
That it seems like when you said the water story, that seems to be the story of Mars. We're almost every question we're asking since the beginning almost is since we started looking at Mars up close and personal is where's the water? How do we find the water? What was it like in the past? Was there life there? That's always where we get to, right? That's always where it is, right? And I know that you as a Martian researcher don't necessarily focus on whether or not life is there. You're interested in the atmosphere, both now and in the past. But there is a bit of information that came out recently about methane going on. Methane ups and downs. What are they called? There's a ton of methane, then it goes away, and there's this sort of like seasonal variance of methane. Is methane the good way to go when we're looking for life?
Well, it's interesting. So life, don't discount it because there's a little bit of that hiding behind all of what we do. So when you think about water, and that whole mantra about follow the water, there's a reason we care about water, and it has to do with life. And so methane was something that was very exciting. We started to hear reports of that back in 2003 about the idea that maybe you had some of this material in the Martian atmosphere. And it's really weird because methane shouldn't be in the Martian atmosphere, not a whole lot of it anyway. It's not stable, it degrades over time, something like 320 years, and it disappears. So if you see it in abundance in the Martian atmosphere now, and especially if you see it in some places and not in others, which means it hasn't had the time to mix around, that suggests that something is producing that methane. And there's only a few processes that do that.
Okay, that makes me really excited.
So there are a few suspects, always with these sorts of things. You've got the potential of having what reactions with hot water and rock in the subsurface. So there's a process there that creates something called serpentinite, which we know a version of it as asbestos, but don't worry, there's nothing on Mars to get cancer. So you can have that creates methane as a byproduct. You can have life, and much of microbial life on Earth can also produce methane as a byproduct. And you have a natural amount of methane that arises from taking apart the organics that fall on Mars constantly. All of the inner planets of the solar system have this sort of constant rain of a few hundred tons of organic carbon per year. It's from interplanetary dust particles. And if you go to a really, really clear place and you look after sunset, there's something called the zodiacal light, which is the reflection of the scattering of the light of the sun off of all of those little tiny dust particles within the plane of the solar system.
That, by the way, is really cool, the zodiacal light.
Indeed, indeed. So what's really interesting about methane, so it's a fascinating molecule, and it can potentially tell us a great deal about what's going on Mars, but we need to figure out how to interpret it. And all of the different measurements that have been made, there's been telescopic ones from the Earth, there have been ones from Mars Express, and we have ones from Mars Science Lab. Except for the MSL ones, all of the other measurements are sort of at the edge of they're sort of coming up towards the edge of what the technology can do, and they all kind of disagree with each other in terms of when the methane happens, where it happens, and that means that it's hard to construct a coherent story. The stuff from MSL is very solid because we intentionally designed an instrument to go and measure methane in situ, but it's still not a clear story, which is interesting. You see these periodic bursts when the methane goes up, you see a bit of a background value, and we're still trying to figure out exactly what that means.
Okay, so if you were to design a mission to answer that question once and for all, where's the methane coming from, what would that mission be?
That mission would be the Trace Gas Orbiter launched this past year by the European Space Agency.
So the work's already done for you.
Exactly. So I'm looking forward when they get there later this year to hear what the answer is. They have a spectrometer on board called Nomad that is going to do mapping of the atmosphere. They claim they can get down to very, very tiny amounts of methane. For those of you who want the figure, it's 20 parts per trillion that they claim that they can get to. MSL can't get quite that low, and it's only in one spot. So if Nomad and TGO can successfully go and map the entire Martian atmosphere and look at how it changes with the seasonal cycle, then we might actually get a good handle on what's going on with this molecule, what's producing it, what's really the methane story. And once we know the geographic and the seasonal progression of it, then we'll have a much better idea of which one of those three theories is correct. Okay,
I have a ton of questions. So I want to bring us out a little bit further. I don't know if we're going to have enough time for all the questions that I have. Do you remember a little while back, and those people listening in, and if you're just tuning in, everybody, you're listening to York Universe here with Jesse, Richard, and John. I'm just asking all my Mars questions right now. And I promise I have solar system questions too. A little while ago, there was these observations made both by originally discovered by amateurs, but then confirmed by Hubble, or at least somehow confirmed by Hubble, of high altitude plumes in the atmosphere of Mars. And we're talking way above where you would expect any atmospheric phenomenon to be happening. You remember that story, right, John?
Yeah, there is there are interesting things that have been seen. So plume might not be the right word. You do sometimes see these very, very high clouds on Mars, and these have been seen from the orbital assets as well. These sort of really high detached hazes, and it's not always exactly clear what it is that's causing these. But I believe you're referring to a paper that came out not too long ago, which suggested that, very interestingly, that all the conflicting reports of methane were all actually correct. And they were correct because they correlated very well in time with when Mars would pass through different meteor streams. So I think that's we don't have the final word on that yet. We can't forget that scientists love to say correlation is not causation. Just because
yes, we do.
Just because things are associated in time doesn't mean that that one causes the other. And there are other reasons to perhaps be a little bit skeptical of this. I would hold off and see what TGO finds next year. If it really is that, then TGO's and the Nomad instrument is the way to tell beyond a shadow of a doubt what's going on.
Does it have anything to do with Aurora, as Black Projects in our chat room is pointing out, and something I've heard before? Has it anything to do with like solar winds and magnetic fields, anything like that?
I've not looked at that specifically. I'm going over to that now. So it looks like it's talking about the MAVEN spacecraft, which is really meant to hone in on the upper atmosphere and really understand the loss rates of things like water. I mean, that's one of the issues when you're discussing the atmosphere, is the atmosphere can go away to space. So you need to understand that boundary. So I haven't seen this specific press release myself, but MAVEN's been doing a lot of very good work. And Aurora and Airglow is something that you do see on Mars. Not nearly as much as you get on the Earth, but they've really been revolutionizing our knowledge of the upper atmosphere of Mars in particular.
Okay, I could follow that line of reasoning with all of the magnetic fields and all that stuff, magnetic history of Mars, but I want to go bigger. I want to jump into the solar system, because a little while ago I emailed you a question that I had, because I was discussing with a friend of mine, Dr. Rachel Ward Maxwell, about what exactly is a protoplanet. We're not talking about dwarf planets or anything like that, which is always the main conversation. But what do you consider a dwarf planet is? And my thought was that things like Ceres or Vesta would be considered protoplanets. And so I emailed you that question. And could you sort of shed some light for all of our listeners on sort of the idea and nomenclature and taxonomy behind all that stuff?
Yeah, this really is a taxonomical thing. I mean, just in the natural world, we always get the full range. When does a giant planet become a brown dwarf, become a star, right? We don't spend so much time there. I think it's because the solar system is here and it's nearby that we have these debates about what is a planet and what is not a planet. So in terms of dwarf planet, that actually has a formal definition under the IAU's guidelines. And places like Ceres fall very cleanly into that. They're rounded by their own gravity. They orbit the sun, but they haven't cleared out their orbits. They're in the asteroid belt, for instance. And Pluto has a similar issue, which is why it is also a dwarf planet. When you're talking about protoplanets, this is kind of a term for the early accretion of the solar system. So we know that we had lots of material that accreted together into planetesimals, and then those planetesimals came together. And there's sort of that intermediary stage between planetesimals and full-on planets, and the name that's sort of been tossed around for those is protoplanet. So, proto meaning sort of the ancestor of a planet, which is where that terminology comes from. Not everyone likes the term protoplanet. Some people have proposed the term planetary embryo as a better term for these. And sometimes these very large bodies do run into each other. We have the moon because of a big oblique collision between the Earth and a protoplanet, though perhaps protoplanet's not the best name for that, since it didn't become a planet after that. So I personally don't don't favor the name of protoplanet for anything that is in the solar system today. It's not the ancestor of any future planet. So,
yeah, it does sound a little bit odd when you're saying it's a protoplanet. You're sort of saying, oh, it's going to grow to something bigger, and it's certainly not going to.
that's sort of where I am with that. And there's no shame in being a dwarf planet.
Not at all. I love the dwarf planets, by the way.
And 2015 was the year of the dwarf planet, with the first visits to Dawn of Dawn to Ceres, and of New Horizons to Pluto.
Yeah, not bad at all. We're doing really good on that dwarf planet stuff. In fact, I would bet that the key to understanding the real next step in solar system understanding and planetary science is really finding all those tiny little things and where those puzzle pieces fit into the grand story that is now what we call our solar system. But we only have 3 minutes left, John, and I haven't let you talk anything about your big project coming up with Dr. Ray J, on branching out into a sort of bigger collection of topics. What's this project you're working on?
Sure, I can give a little blurb about that. So in Canada, we have a great program that is run by the Natural Sciences and Engineering Research Council. And what they do is they provide money to go out and to basically develop the next set of researchers, the people who will be on the cutting edge. And they advertise for specific concepts. What are you going to do that's different and new and exciting to really get Canadian researchers out there? And so what Ray and Ray is the principal on this. It's he led the proposal, and he brought together some fantastic people, let me tell you. But what we came up with was the idea that we would take the people who did the planetary exploration, folks like me, and to get them together with the people who do exoplanetary astronomy, and to combine both of those with the people who do the design of instrumentation and the design of spacecraft, principally in industry. You put all those together and get us talking to each other, and you never know what discoveries are going to pop out of that kind of collaboration. All of these different fields, I think, can learn something from the other one, and that'll be a great incubator for the next generation of talent. The program's called Technologies for Exoplanetary Science. It's centered at York, but we have people participating all across the country, and in fact, all around the world in this particular program. It's going to be a fantastic 6 years.
It sounds like you've really taken a step to shape the researching world that you're a part of.
Well, I like to think I help with that. But it's definitely Ray J has taken the lead on this,
okay.
And he's very good at what he does.
Okay, well, I would love to really dive in. Maybe we should come and get an update from that a little bit later on, but I only have 45 seconds left, so I should probably close this out. John, thank you for joining us tonight. This has been a really great discussion.
Thank you for having me.
No problem, and I'm sorry to say we do have to close it out, everybody. You've been listening to York Universe. We're here in Toronto, Ontario, Canada, at the York University Astronomical Observatory. Of course, you can head over to our website because the chat room is still open at astronomy.blog.yorku.ca. You've had myself tonight, Jesse, and Richard, who's been working diligently in the chat room, trying to handle everything over there. If you have any questions at any time, hit up our website, hit up Twitter, or hit up Facebook. Thanks for everything, everybody. Have a good night.
Bye.
Bye now.
We hope that you've enjoyed this program from AFM Radio, the broadcast service of Astronomy.fm. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original